I got it. Hello, Nur. Garlic is in a space, traveling. Oh, you can't hear me.
Hello, Professor.
Hi, Nur.
Hello,
Hey,
Professor. Hey, Professor.
Garlic, can you hear me? Okay. Yeah, your audio is off. Hi, Joe.
Good morning, Professor.
Okay. Seems like you really like this San Francisco. Don't you want to change to like Sudan or South Africa or maybe Amazon in Brazil? I guess you're just kind of lazy to change your background. Let me see. So, since Garlip and Cheu, both of you are here, and then both of you are supposed to give a presentation about the dentistry and also gynecology. So since next Tuesday, I will be out of town. So next Thursday, you two can prepare your presentation. And then I guess it seems like 1.5 hours is enough for both of your presentation. And if we are lack of time, then maybe we can extend the time for the another week or so. So Khalid for the dentistry and also Jeu for the gynecology. Okay.
Hello, Professor. My topic was urology. I make presentation for this topic.
Really?
Yeah.
I think I changed it, but okay. So did you already prepare something?
Yeah.
Really?
I prepared this presentation.
Really? Okay. Jeu, what was your original topic?
I think my previous topic was
Neurosurgery?
no gynecology. I'm not sure, but
I mean, you can choose.
Then it is okay that I will prepare the dentistry.
Dentistry?
Yes.
Oh, okay. So urology for the garlic, and then Jeu will prepare for the dentistry. Okay. All right. So next Thursday is basically May 6th, and then May 4th, my lecture will be on YouTube video. Okay. Is there anyone who visited YouTube and watched the video for the last lecture? Maybe not. It was the last lecture, so you don't need to. Okay, so it's 9:03, so we can start. So we will finish the thermal interactions, which we were discussing last lecture. So for the LITT, the full name was laser-induced interstitial thermotherapy, so LITT, LITT. And then most of this LITT application is on the tumor treatment. So when the tumors are a little bit deep inside of the tissue, and then you cannot apply for any, I think that, yeah. This is kind of minimally invasive surgery. You do not have to really make an open space and then giving a LITT, but the left case is actually showing the open surgery. So you can see the kind of fiber is going in to the tissue here. But it also can be applied to the retina and also brain, and then prostate, and liver, and uterus, and then varicose veins. And then this is one of the minimally invasive surgery. But most important application is treating the malignant tumors in the uterus or benign prostatic hyperplasia. So to do the LITT, you are going to place laser applicator, which is basically the optical fiber. And then, but this optical fiber is a little bit kind of different from the normal optical fiber. It is having, so optical fiber in general has a core, and then outside is cladding. Manar, do you may remember about the reflection? And then in some cases, the light will be reflected kind of 100%.
I don't remember.
Yeah, but do you may remember about the Snell's law?
Yes. It
Okay.
depends on the medium.
Uh-huh. So instant
So
angle and then the reflected angle are having a relationship depending on the refractive index of two materials. So here is same thing. Core has a little bit higher refractive index than the cladding. So because of that, when the light is coming to the core, if it comes parallel with the core, then of course it will travel, go straight. But not all the light are coming in, parallel with the core, but some are going to have an angle. So that angle is the range of the angle that this core can collect the light, and then sending the light within the core is called as an acceptance angle. So when the light is coming in to the optical fiber within that acceptance angle, and then the light is going into the core, and then the light will be reflected at the surface or boundary between core and cladding, and then it doesn't go out. but comes back into the core, and then that continues. And then this is called as a total internal reflection. Total internal reflection. And then this is how optical fiber can deliver light by using this optical fiber for the long distance. But this LITT is optical fiber, but most of cases, optical fibers are basically sending the light into the like this direction, right? But as you can see in this kind of figures or images, many of cases we like to send light to the side of optical fiber. So they are having some materials at the tip of the optical fiber. So here is the optical fiber, and this is the end of the optical fiber. And this is having kind of diffusive medium. It can be the surface grounded in quartz, like that. So that when the light is coming in, it can go to all the directions. So like this example, you have an optical fiber catheter inside, and this one, this area is also going to have a light. So that it can treat large area. Since the purpose of LITT on the tumor is basically killing the tumor, so you can actually provide high energy to generate high temperature. However, you know that too high temperature can make the carbonization, which we do not want to have. And then we just need to kill tumor cell. So to do so, we just need to have about 60 Celsius degree or higher temperature, which is the enough temperature to cause the coagulation, so that this tumor cell will go under necrosis. By doing this process, because of that temperature, blood vessels surrounding that area, like here or here also, they will be also kind of simultaneously coagulated. So since blood vessels are coagulated, so it can minimize the bleeding. And then that is the one of the advantages compared to the conventional surgery using the scalp. That's because most of the cases, the tumors are highly vascularized, meaning that there are a lot of blood vessels. And the bottom examples are showing benign enlarged prostate, which I think now Carly will present about the urology. So in the prostate, as age is getting higher, so you can see that the prostate tissue is enlarged, and then they can block the uterus here, so that so that the urine cannot easily flow from here. Sorry, not the uterus, but urethra. So here. So to do the LITT, you can use the ND-YAG laser, which has a 1064 nanometer, or diode laser 800 to 900 nanometers, because this wavelength, it can go deep inside the tissue, so that with the same applicator, if you are using maybe visible range, then you may treat this much of the tissue. But by using those wavelength range, you can treat much larger tissue. So example, continuous wave laser with 1 to 5 watt and then giving about a few minutes. Then you can have about 4 centimeter diameter of the tissue can be coagulated. And then for doing this kind of LITT, the accurate estimation of the final damage zone is very important, especially in the neurosurgery. So this is very natural. So you have a tissue and then you have a tumor like that in the brain, especially, and then you place optical fiber. Maybe it can be 1 or it can be 2. And then you are going to make a treatment. So you will treat here and here like that. But our purpose is to give a whole tumor treatment so that they will try to give more time so that all the tumor can be coagulated. But if you are giving a little bit too long time, then that can actually damage much larger than the tumor. And then you know that outside the tumor, this is normal brain. And then if you are giving a damage to the normal brain, then you will lose some kind of functions, which can be really bad. So when you are doing LITT, it will be good if you can have a very precise estimation of how large area will be coagulated by doing the LITT. So let's say you just target around here. So they minimize the normal brain tissue but basically treating the whole tumor. This is this issue is same for all the heat treatment or cryotherapy. Sometimes there is a treatment not generating the heat, but giving the cold. So as you can imagine, cells cannot survive in a high temperature. At the same time, cells cannot survive in a cold temperature. So either making a heat or either making cold, both will treat or basically tumor or killing the cell. In either case, estimation of the precise area which will be affected by cryotherapy or the heat therapy, thermotherapy, is going to be very important. So this spatial extent of the damage zone will be depending on, of course, how much power, how long you're giving the laser, and then what is the geometry of the applicator. So the applicator can be designed in multiple ways. Some are just kind of forward, some are side, and some are maybe both. So like this way. So depending on the geometry of the applicator and the exposure time and the power of the laser, the damage zone will be also different. And also important thing is the optical property of the tissue. So how long, how deep will be the optical penetration depth for the tissue, and then what will be the thermal property of the tissue, so that it has whether it has a high a thermal conduction rate or the heat conduction or heat dissipation rate. So since near infrared laser can go deep in deep tissue because there is a high scattering compared with the obtrusion. And then especially it can go deeper because heat conduction is smaller than the optical penetration in the NIR range. And also the laser applicator's surface has a kind of scattering surface, not the focusing optics, which means that this applicator tip is not making some focus, but rather it has a scattered surface, kind of rough surface, so that it can actually deliver light into the whole 360-degree range. So when people first developed this LITT, they basically used the bare optical fiber. And then the problem was at the end of the optical fiber here, only this area was having very high power density. So that caused carbonization for the surrounding tissue when you are using this bare optical fiber. And then the Rogan, they made the isotropically scattering laser by using the rough surface. So normally having 400 micrometer diameter, and also the catheter is transparent to allow the light to travel to the surrounding tissue. And then the surface of fiber can be etched by using the acid chemicals. And then that makes isotropic scattering at the interface of applicator and tissue. And then you have seen this one. The procedure is this. So you place the catheter, which is this one, the transparent catheter into the tissue that you are targeting. Since the light will come out here, so you want to place the catheter just within that range. And then you are inserting optical fiber with a frosted surface to make the isotropical light delivery. And then you basically turn on laser. And then the laser will come out. And then it will generate heat. And then those tissue will be basically going to die. So once you are done for the laser exposure, you can pull this fiber back. And then when you are doing this one, you can have a multiples of this catheter, but do not exceed 1.5 millimeter distance between the puncturing canals. What they mean is that when you are using multiples of this optical fiber treatment, between those catheter, you need to have a less than 1.5 millimeter separation. But I think that this is also depending on the properties of the tissue and also the laser wavelength. So you have seen this one already before. So when you are using longer than 1 microsecond, then the temperature rise during the laser on. When you turn off, it goes down. And then especially the temperature distribution along with the radial distance from the applicator exit, which means that when you have a catheter and then from here to this direction is the radial axis. So from the center of the core, how wide, how kind of far from the center of the optical fiber. So 5 millimeter, 10, 12, 15, 20, and then 30 millimeter. And then when you look at the temperature change along with this radial distance, there are three examples here. The first one is conventional hot tip. And then the second one is normal LITT applicator. Third one is cooled LITT applicator. So conventional hot tip means that you can basically have a kind of tungsten wire generating the heat, and then you measure temperature along with this R direction. And you can see that it goes down immediately. And then the threshold coagulation is 60 Celsius degree. So you can see that's about like 7 millimeter. If you are using normal LITT applicator, then that's a little bit longer, about 9 millimeter. For the third one, cooled LITT applicator. So this one, you have a optical fiber with a catheter, the applicator, and then you do have the catheter outside. And this catheter is actually cooling down by the water or cold air so that it can lower temperature right next to this catheter. So you can imagine without having cooling of the catheter here, the temperature right at the boundary between catheter and tissue will be the highest. However, by having the cooling, either using the air, cold air, or water, you can actually lower temperature in this area. So that you can see the right next to the catheter temperature is actually lower. And then it goes to the maximum at some certain distance in here, like 2 millimeter. And after that, it goes down. By having this way, you can see the radial distance for the 60 Celsius degree is now about 12 millimeter. So using this cooled LITT applicator, you can increase the tissue volume that you can that you want to have a coagulation. So far, we only considered absorption property of tissue when we are handling thermal interaction. And during the LITT, coagulation occurs, and then by having this coagulation, it changes optical property. It changes tissue to become more highly scattering, so that the color changes, and then because of this high scattering here, the penetration depth can be also reduced. So this is the actual problem, because in the original state, we can estimate about what can be the affected area or what can be the affected volume within the tissue. However, when you are doing treatment, the tissue changes optical property, and then that changes also thermal property, so that it becomes hard to predict precisely. So instead of giving a single LITT catheter inside, you can use a multiple LITT treatment. So you can have let's say you have a single laser in and then beam splitter using 3 beam splitter. So dividing here, and then here you are dividing also 2. So one comes here, the other one goes to here. And then another beam splitter divides into 2. So one comes here, the other one comes here. So you can have a 4 output from the single laser input. And then you can have a 4 fiber catheter to place in the tissue at the same time. And of course, if you are dividing this into one more time, here also one more time, then you can make more, optical fiber output. But you need to be careful for the power for the each output needs to be same. And this photo shows the examples of when you are using multiple LITT treatment. So here you have 3 spots, and then it makes kind of triangle shape. And then having a 4, so they're making kind of rectangular shape. And then for another 4 here, another 4 like that way. The applicator of the LITT is having the treatment on the surface. So here we can see, depending on the how the surface is treated, you can have a simple light delivery like that. But if you are having kind of a highly isotropically scattering materials, then you can have a more wider range of the light delivery. And then one of the material is raw quartz, and to have a volume scattering because it has a very tiny gas bubbles inside, and then they can serve as a scattering center. And then this one is one of the examples of using isotropic scattering applicator for the LITT. So laser comes in, and then it delivers light into 360 degrees. So here's a summary for the thermal interaction. So main idea is that we are giving the laser to the tissue, and then the tissue is going to observe the energy of the laser, and then due to the vibration each other, it generates heat, and then that heat can cause the damage to the tissue, especially when the temperature is going beyond the 60 Celsius degree, then it starts to cause the coagulation. And then 100 Celsius degree vaporization, and then all the water is gone, and then carbonization. And then if you keep increasing temperature, it can cause the melting of the tissue. So typically, you are using CO2, Nd:YAG, erbium-YAG, chromium-YAG, and argon ion diode lasers, especially in the kind of 1 micrometer or higher range, because water has a higher vibration energy in the longer wavelength. So typically, pulse duration time can be longer than 1 microsecond because you have seen that thermal relaxation time for the water at the 1.3 micrometer was 1 microsecond. So if you are giving the longer than 1 microsecond pulse, then that gives enough time for the heat to transfer from the original location to the surrounding tissue so that it will cause the damage to the surrounding tissue. Typically, power density is 10 to 1 million watt, 1 megawatt basically per centimeter square. So applications are coagulation and the vaporization and the melting, thermal decomposition, and the treatment of the retinal detachment, and then toasting. Okay, so we are done with the thermal interaction, and then we can move on for the next application. Application interaction. So far we have done for photochemical interaction and the thermal interaction, and then this is the third one, photoablation. So Noor, when you see this name, what do you think?
I think we use this in order to remove cells, like ablate the tissue
Mm,
using the laser.
mm. And more. Okay, your best friend Manar. So can you add more thinking about why the name is photoablation?
We have no more idea.
That's okay because it's hard to imagine from just the name itself. How about you, Garlic? Hmm? No. Okay. It has a name of the photo, but we all know that when you are using the laser, that's the photon. So why it has the name of the photoablation? So photochemical interaction was basically, as the name says, that between the photon light, and then light is going to cause some chemical interaction in the body, which was actually at the end the production of the reactive oxygen species in the photodynamic therapy. For the photoablation, so as Nur said, ablation is basically removing the tissue, but by the photo, so using the light, remove the tissue. Okay, then it can be actually anything that you are using the laser, and then you can remove the tissue when you have a high power. But here later you will see that it has a name of the photoablation because you need to have a specific wavelength and also with a specific the duration time for the laser to do the photoablation. So in the photoablation, important thing is that the energy that photon has versus the binding energy of the molecules in the tissue. So if the photon energy is higher than the binding energy between each molecule, then you can cause the photoablation. But if not, then it may not actually do any ablation. So let's look at this same graph again and again. For the photochemical interaction, thermal interaction, more high power and a little bit shorter exposure time, but longer than 1 microsecond. Photoablation is right here. So to do the photoablation, you need to have a little bit higher power density than the thermal interaction, but also shorter exposure time. Wow. So when you see this kind of photo, what do you feel, Jill? Jill, what do you see in this photo?
I think this is the part of the tissue after photoablation.
Yeah. But I don't know whether you remember about the thermal interaction case. What do you think is difference between this photo and the thermal interaction, thermal ablated tissue photo? Of course, this is not color, so it's kind of a little bit hard to compare each other. However, there is a big difference actually. So maybe I can open so in the thermal interaction, let's see whether we have a photo. So like this one. So between these, I don't know whether you are seeing this one. Do you see this? Okay. And then now, how about, do you see this one also? Okay. So you can see it's quite different between this thermal ablation versus this photoablation. I'm sorry. So this one, as you can see, it has some kind of black color here. This one is also cornea, human, the eye cornea. And then using the thermal interaction, you can see that the surface of those are black, which means that they are carbonized actually. But this one is very clean. You do not see the surrounding boundary here are kind of carbonized. And then you can also see that this surface is so clean, so sharp. So that's the difference. So photoablation doesn't really allow the carbonization or the coagulation or hyperthermia surrounding tissue of the ablative tissue. So this tissue was here, and then later, and then they are gone. And then the leftover tissue is so clean. So that's the huge difference. So example here is done by argon and fluoride excimer laser using 193 nanometer, very short wavelength to the cornea. And then you do not really see coagulation or vaporization. And then Srinivasan and then Mayen Banton in 1982, they first discovered this photoablation. At that time, they called this as ablative photodecomposition. And typically, the light intensity threshold should be higher than 10 to 7. So 10 megawatt or 100 megawatt per centimeter square at the nanosecond pulse duration. And the one good thing is this depth of the ablation depends on the pulse energy and also absorption depth. And then this is very predictable, which means that when you are giving a same pulse energy and with all the same parameters for the laser, and then if you give a single pulse, and then maybe single pulse can cause 10 micrometer ablation depth. And then if you're giving 10 pulses, then it will be 100 micrometer depth. So you can control the ablating the tissue very precisely by controlling the laser parameter. So that's good thing, because when you want to do the cornea surgery using the laser, basically you need to cut off tissue. And then you need to have a very precise prediction of how much will be cut off by using how many pulses, like that. So advantages of ablation, photoablation, is a high precision of the etching process. Let me add this one, photoablation. So that it has a very good predictability. And because it has a shorter pulse duration time, so thermal damage to the surrounding tissue is very minimal. And then you can apply this photoablation to the refractive corneal surgery and also skin rejuvenation. So such as the remove the wrinkles and spots or the aged skin. I want to have the skin rejuvenation to remove the wrinkles around the eyes. Organic polymers. So before we actually move on here, let's look at this polymer first. So organic polymers are basically the large molecules, and then it consists of more than 1,000 atoms. And then in the tissue, most of atoms are basically carbon, hydrogen, oxygen, and nitrogen. And the monomer is having about up to 50 atoms. So polymer is, of course, as its name says, that multiple of the monomers. And the bottom is showing the examples of the polymer, PMMA or polyimide, like that. So people were actually modeling this photoablation using the materials of the PMMA, polymethyl methacrylate, PMMA. And then they modeled this photoablation using PMMA by the Garrison and the Srinivasan in 1985. And the theoretical background was Newton's equation of the motion. So Garlic, do you may remember anything about the Newton's equation of the motion? Manar is looking at nude. It's okay.
After every action has the opposite reaction.
Yeah, that's one of that.
Yeah, third rule.
Right. And then how about, actually there are three.
Yeah.
Yeah, it's okay. I also forgot. Whenever I kind of finish the study, I forget. There was, I guess, when did you learn Manar? Was it like middle school,
Something like that.
right?
I don't remember it.
Yeah, I think that there was maybe in the early chapter for the physics class. Okay, anyway, so because of that, I'm very, how can I say, very, I don't know, good, not good, but generous to go back what are the Newton's equations of motion in the next slide. So they assume that the monomer, this PMMA, is having many monomers. And then the monomer are structureless unit. And they are simply holding together by having kind of attractive force. And then it makes the polymer. So when you are giving the laser to this polymer, then what happened will be basically this polymer will have a laser, and the laser energy will excite each monomer. And then before they were having attractive force between each monomer and monomer like that. But since now the monomer is having energy, and then they are turning into repulsive state. So since before it was attractive, now it's a repulsive state, so that the volume of the same polymer will become increased, enlarged, and then it will actually make the transfer of the momentum, and then they are going away. So that's the ablation process. And then I use this example in the class like that. So let's say if this is not online, if this is the classroom, and then I'm here, and then I'm just gonna keep talking, and then you guys are sitting on the desk. So since Manar likes me, so she stays close to my position, and then Nur, and then maybe Garlic here, Jehu, like that. So I'm kind of teaching a class in the classroom. And then you feel like, oh my God, what he is talking about, I cannot understand. Very sleepy. Oh my God. And then suddenly, all of you were having a, what is it? What is it? What is it? The 복권, 제우. What's the name?
Oh, lottery?
Yeah, you bought the ticket for the lottery, and then you found that all of you got the winner, the first prize winner, and then the money is, I don't know how much will be. If the money is like $1, then you can nothing. However, if the money was like $1 million, Garlic, what will you do? If you won the first prize of the lottery and then you got 10 million, not 1 million, $10 million, what you will do?
I just shouting the one.
Shouting and run? That's it? Are you going to keep study? So that was my question. I guess maybe here Manar, Nur, Jehu, and Garib are so excited. Oh my God, I got $10 million. Oh, I don't need to study anymore. I will just spend the money. I will just, tour in the whole world. So I guess nobody will stay in the classroom. Yeah, let's go out. Yoo. And then I'm staying in the classroom alone. So that's happening when there are multiples of the monomer as a polymer here, and then suddenly there is a laser. In this case, the money, $10 million. So when the laser is coming to the polymer, and then it gives energy to each monomer. Before, they were attractive. Now, with enough energy or $10 million, nobody wants to stay in the classroom. I will do whatever I want to do. And then they will be going out. That's the photoablation. So I guess this can be a good example of how you can understand what's happening for the photoablation. But here, the key point is the amount of money. You will go out because you got $10 million. If it was $1, it's just nothing. Maybe $10, not better than nothing. Maybe $100, oh, good. I can have a maybe good, dinner, maybe 2 times or 3 times. If that was like $1,000, That's very good, but I may still need to, study harder so that after graduation I can make more money. If it was $10,000, okay, I will still study. $100,000, oh, that makes headache. Oh, should I continue to study or should I just go out to use the money, right? And then if it becomes maybe more than $1 million, then you may have no, headache, no struggling to do what to do. You will just go out, right? Same thing here for the laser. All the monomers are having their attractive energy. And then if you are giving laser just below the attractive energy, then they will be just stay there. You need to give something higher than that attractive energy. Then finally those monomers will be going out. And then ablation is happening. So there is a threshold. So that is the important thing in the photoablation. So let's continue on here. So for the modeling, what they did was that they assumed those monomer is basically a face-centered cubic crystalline array. So face-centered cubic means that they have an atom in the center of the cube. So how many atoms in this FCC? So 1, 2, 3, 4, 5, 6 faces, right? But each face is having the half is shared by another one. So it has only half. So you have 6 atoms at the plane, but actually you have 3 atoms in total. Anyway, the density of the crystalline was assumed to be 1.22 gram per centimeter cube. And the monomer mass was 100 Dalton. And the lattice constance was 0.81 nanometer. So, which means that this was 0.81 nanometer. So now before we continue, let's go back to the Newton's law of motion. So the first law is law of inertia. So when there is no external force is applied, then the moving object will continue to move and then stay in a one position object will stay there. And then the second law is basically F is equal to ma, which is very famous equation. So the force is mass multiplied with acceleration. And then since those are vector term, so it has the bold font. And third law is the Garland mentioned about equal to the opposite reaction. So F, the force between A and B is same as force from the B to A, but in a opposite direction. So here we will also use the this modeling, and this is showing the examples of the cubic lattice. So this is the primitive cubic, which has the 6 faces. And the body-centered cubic means that it has one atom in the center of the cube. Face-centered cube means that it has an atom at each face. So it has 6 faces. So the total atom number is going to be 3 atoms for this case. For the body-centered cubic, it has a single 1 atom. And also, it shows the dissociation energy for the chemical bonds. So between carbon and oxygen double bond, the energy is 7.1. Between carbon-carbon double bond, it is 6.4 electron voltage. But for the carbon nitrogen single bond, it's only 3 electron voltage. So compared with the carbon to nitrogen single bond, carbon-carbon double bond is having more than twice stronger binding energy between each other. In the tissue, the main attractive force of the monomer is going to be the carbon-carbon bond, which is corresponding to about 3.6 electron voltage. And then repulsive force between monomer is going to be inversely proportional to the R, to 12th power. And here R is the mean distance of the two monomers. So by looking at this one, as R is getting smaller and smaller, the repulsive force is getting very, very high. So with all the assumptions above, the figure 3.32 is showing the simulation results from the photoablation. So here you have a lattice for each monomers, and then you were basically giving the laser energy to this volume. And then those monomers got laser energy, which is high enough to break down this binding energy between carbon-carbon or carbon-oxygen, nitrogen-hydrogen. So let's say that the laser energy was having maybe higher than 7 electron voltage. Then those monomers will have enough energy to change from the attractive force to the repulsive force. And then within like 4 picoseconds, they will be all going out and be separated. So here, actually, the important thing is this one, energy. This energy is not simply like how strong light intensity is. It's not. This energy is coming from the nature of the light. So we all know that the wavelength going down, frequency goes up, and then the energy it has is also going up. So for the UV range, that's normally about like 230 to about 430 nanometers. This is also very strong energy. And then sub-UV range, it becomes like soft X-ray and the hard X-ray and the gamma ray. They are having very, very short wavelength. So this binding energy is kind of fixed number. And if you want to dissociate this binding energy, you need to have a photon energy which has a higher than this energy. Otherwise, this will not happen. So here, let's say carbon-carbon binding is 3.6 nanometer electron voltage. So by using the previous example I mentioned, let's say JU is, how can I say? So not very greedy. So he's okay if he can have like $100,000. Then he's so happy. Oh yeah, I got $100,000. I will just go out. However, Garlic is a big businessman. $100,000 is nothing for me. He wants to have at least $10 million. So that's basically this binding energy here. So Garlic can be 7 electron voltage, JU can be like 3.6 electron voltage. So each person has a different the level of the greediness. And then same for the monomer or atom-atom binding energy. So you need to provide higher than those binding energy to break down so that they can be dissociate each other. So assume that two atoms, A and B, they are bound by a common electron, which is the covalent binding. And the corresponding energy diagram is shown in figure 3.3. So you have a A and B bound. When they are in a lower energy state, ground state, you can see the radial distance when they are far, and then at some certain distance, it has the lowest energy. And then if it becomes more closer each other, then strong repulsive force will be happening so that the energy is going up. For the far, you will have a more attractive force also. So there is some point that it has the lowest energy between A and B, the distance. So when you are giving the laser, and then the laser provides energy to this AB molecule, which are in the ground state. And then, of course, there will be multiple energy levels within this ground state because of macromolecular structure. So you can imagine this as a multiples of the vibrational energy in a single atom. And then with the laser, and that provides energy, and then make a AB molecule to be excited state. So once they are excited state, as you can see, within the same distance, they are so high compared with this. And this is corresponding to the repulsive energy shown on here also. So what's happening is that they will try to be separated. We should not stay anymore together. We got enough money, so we need to have our own life, and then bye-bye. So that's happening. So here the Frank-Condon principle can be applied. And this principle means that the radial distance between two atoms, it will not be affected during the process of excitation. And that's because of the electron mass is so small. So even though electron is absorbing light energy and then to be excited, however, it can keep the distance between A and B so that the transitions are favored as indicated in figure 3.3. So instead of this ground state, getting the energy, and then maybe it becomes going into like this way, but it goes to here. And then in a excited states. So from here, what you can see is as the radial distance between A and B is getting farther and farther, they are more stable, mean that lower energy. But when they are in the getting close to each other, then the energy between A and B is too high. So for the ground state, within this distance, they were happy because the energy state was low. However, after observing the laser energy, the energy of A and B binding became too high. And then they want to go lower. And then to become energy lower, the only way is the radial distance needs to be increased, which means that they need to be separated. So the probability of such transition is increased if the maxima of the corresponding Schrödinger functions of the initial and final states coincide at the same radial distance. What they mean is simply, even though when the laser energy is being observed, the radial distance between A and B has to be in the same distance at that moment. And then they has to be going separate to lower the energy from here to go down here. And then to do this, all the effects here, the UV range is possible to do because it has a high enough energy so that the electronic state exceeds the bonding energy of the two molecules so that the molecules will be dissociate each other. So two-step process of the photoablation is, the first one is excitation. So getting the light energy, AB is excited. And then once AB becomes excited states, then they do not want to be here anymore. They want to go down to the lower energy state. And then the way to go down to the lower state energy is they need to be separated. So A and B, and then in that process, there will be some kinetic energy will be also come out, and that this is making A and B to going away. So table 3.8 shows the dissociation energy of the chemical bonds, which you have seen already. And then the right side, table 3.9 shows the photon energy of the specific laser wavelength. So with the argon fluoride laser has a 193 nanometer, and then that corresponds to 6.4 electron voltage. And then you can see that that can be enough to separate all of these except carbon and oxygen double bonding. So that's why the photoablation source is limited to UV range, UV lasers, and typically excimer lasers. So Srinivasan and then Mayen Banton in 1982 and then Brannon et al. In 1985, they were modeling those, and then they also have shown that photoablation is wavelength dependency. So shorter wavelength, you can have a smaller molecular weight. And then 193 nanometer laser can make a smooth surface compared with a 248 nanometer laser. So here, shorter wavelength laser means a smaller molecular weight. Then what they mean is you have molecules, and then let's say it's a little hard to explain, but between each kind of monomer, there is a bonding energy, right? And then when you are having, let's say, 193 nanometer, this is enough to make each, it's A, B, C, D, E, F, G, H, each of the monomer to be separated each other. However, when you were giving 248 nanometer, what can do is not separating all together, but maybe AB and CD and EF and FGH like that. So a little bigger size of the monomer will be separated from each other. So that's why when you are having longer wavelength, the surface after removed from the polymer will be more rough. And also for the photoablation, there is a threshold intensity. So you need to have a more higher than some specific threshold. Otherwise, this will not happen. So higher than the threshold, then ablative depth depends on absorption coefficient of the tissue and also intensity of the instant laser. And these are relatively well predictable. So higher than the threshold, then ablation will happen. And then when the ablation happens, it makes a sound like that, sound, and visible fluorescence, like bluish color, like that. So number of the applied pulses has a linear relation with the total etch depth. So if single pulse has a 1 micrometer etching, then 10 pulses will have a 10 micrometer etching depth. So you have a precise control of the how much you want to remove the tissue. Ablation depth per pulse is reproducible, and that is also predictable. So that in general, within 10% of the predicted depth. So if you were expecting 10 micrometer, then the actual will be 9 plus minus 1 micrometer range. Sorry, 10. So it can be 9 to 11 micrometer. This was your prediction, and this can be your actual etched depth. So table 3.10, it summarizes the principle of the photoablation. So you need to first have absorption of the high energy UV photon so that it should be higher than the threshold. And then it will make ground state to the repulsive excited states. And then in the excited states, they want to have a lower energy. And then only way to become lower energy is making larger radial distance between A and B. So bye-bye. And then shoo, A, B, shoo, going away. And then they become stabilized. And this can be shown as an ejection of the fragments. And this is not actually causing necrosis, it's actually removing the tissue. And this is the ablation. And this shows the examples of that for the photoablation using the human cornea. On the left is fourth harmonic from the NDYLF, which has originally 1053 nanometer. The right side is second harmonic. So second harmonic from 1053 is half of the wavelength. So it will give 526.5 nanometer. For the first harmonic, it will become 263 nanometer. And here you can see the huge difference. With the 526.95 nanometer, you can still make the tissue ablation. However, that is from the plasma-induced ablation. And then for the 263 nanometer, you have a photoablation because this one has a high enough energy to break down the bonding energy of the tissue here. So you can see for the macroscopic, image, the left one is kind of very smooth. Right side one is like, you were farming on the ground like that. And then if you have a zoomed image, also you can see that the photoablation makes very smooth surface. But plasma-induced ablation caused like, oh my God, it's not smooth anymore. It's very, very rough. Some places deep, some places not. So this is showing that the importance of the choosing the short wavelength to remove the tissue by having ablation process. Okay, so this is the end for today, and then we will finish the other one on next Tuesday, but by the YouTube. Okay, so have a good day, everyone, and then enjoy the lunch. Okay, bye, everyone.
Thank you, Professor.
Mhm.